Okay, so today we're going to talk about acceleration, acceleration in 2 dimensions without friction. So now, I know that of course there's always friction, okay? Of course there is. But I want to teach you how to do this without friction first. And then when I do throw in friction, it'll be a little bit better, okay? Now, I've already brought in the questions from yesterday, the 2 without friction from yesterday. So I'm going to go ahead and, again, I'm going to go ahead and read this to you. It says, a ball that weighs 30 newtons is rolling down a hill with a slope of 20 degrees. What is the net force acting on the ball? So this question is going to change a little bit. And we're going to say that this question is, what is the acceleration down the incline for the ball? Okay. We're just going to assume no friction. So let's do this without friction first. All right, so let's draw our free body diagram. Everything's fairly the same. The only thing that's going to change now is that we now have to do one more calculation on top of everything else. But I'm kind of doing this just to kind of review the process of how to do this. If you didn't catch it yesterday, hopefully if I teach it again today, maybe you'll catch on this time. So it's a little bit of me reteaching, which is necessary sometimes. Okay, so here's our inclined plane. Our incline is about 20 degrees. I'm going to go ahead and mark that. So that's theta. Oh, I'm still in the wrong thing. Okay, so here, theta is 20 degrees. Now let's go ahead and let's get our ball here. Good enough? Okay, let's go ahead and do the free body diagram. Everything that goes straight down is FG. Perpendicular to the surface is FN. Straight down to FN. From FN is FG of Y. 90-degree angle between F and Y. FG of Y and FG of X is going to be 90-degree angle between FG of X and FG of Y. This angle here is also theta, which means that's 20 degrees. All right, the only other thing that we still need to draw is the things acting up or down the slope. That's all that's left to draw. So now remember, we're supposed to put FG of X up here. We've got to practice that. So we're going to draw FG of X here. And since I have no friction, I have nothing acting against the motion. And so that means we know the net force is this way. So that's it. So the next step after we draw the free body diagram is to write the net force equation. Now, because I do not have anything acting against FG of X, then F net is just equal to FG of X. And that's it. Okay, so then we just calculate, go ahead and calculate FG of X, which is going to be mass times gravity sine of theta. FG of X is always mass times gravity sine of theta. So then we just put our stuff in our equation. FG of X is equal to mass times gravity. Well, this here is already in newtons, so that already is mass times gravity. So we're just going to put 30 straight in. Had that said kilograms, though, then that would have been 30 times 9.8. But since I said newtons, we just put 30 straight in there. So it's 30 sine of theta, which is 20. The calculator will give you, let's see, 30 sine of 20. Is 10.26, but let's just do 10. Let's just do 10 newtons. That's what we're going to do. So that's great. We found FG of X. That's wonderful. Okay, but that's not our end answer. Okay, we want the acceleration. Now, we know that F is equal to m times a. Well, what I didn't teach you so far is F net is actually equal to m times a. So if we have F net, which is what we just discovered because Fg of x is equal to F net. Okay, so 10 newtons is equal to F net. So if we have F net, which is this one, and we have the mass, well, we kind of do, because this is the weight, and we could easily figure that out, then we can calculate acceleration. Okay, because acceleration, the formula for acceleration using F net is going to be F net divided by mass. So we have F net already, so that's 10 newtons divided by mass. Well, mass is in kilograms. I don't have anything in kilograms, but I do have the weight. So remember, the weight, which we put in this equation as weight as 30, is mass times gravity. This is mass times gravity already. And if it came out to be 30, then I have to do, that's weight. So weight is equal, I'm going to do this in a different color. I'm going to do it over here in this little area. Weight is equal to mass times gravity. Well, the weight was 30 newtons. So if I rearranged that and said mass, rearrange that equation, mass is equal to weight divided by gravity, then I can get the mass from that. So that's 30 divided by 9.8, which is, I don't know, 30 divided by 9.8, 3-ish. We're going to do whole numbers. 3. Okay, this is in kilograms because this is a mass, so that's in kilograms. So we can put that down here, 3 kilograms. So now you just do 10 divided by 3. Acceleration is 10 divided by 3. 3.333, I knew that. 3.333 repeating, we're just going to do whole numbers. Now, this is acceleration. We did newtons divided by kilograms. So let's do units real quick. I'm going to do this in a completely separate color. I'm going to do this in purple. Let's do units for just a second. So a newton, I'm going to do this down here in this little area. So a newton, because we did newtons divided by kilograms. A newton is equal to a kilogram meter per second squared. And if I divided it by a kilogram, all I'm left with is meters per second squared, which makes sense because acceleration is always meters per second squared. All right, so my end answer is acceleration is 3.3 meters per second squared down the incline. And that's it. You're done with that question. That is it. That is your end answer. That's the final answer. You're done. Now, let's do this other one. Okay. So it says this is frictionless question because we'll do acceleration with friction next week. It says friction. You push frictionless. You push a box up an incline of 22 degrees. The box is a mass of 100 kilograms. You push the box with an applied force of 3 newtons. Now I'm going to go ahead and change this question. I don't want to know is it strong enough anymore. I want to know what the acceleration of the box is and then the direction of that box. I erased too many things. I got to put some of this back. Okay. What is the acceleration of the box? Now, we knew that from the other day when we solved for this one, that yes, you were pushing the box up the incline. You pushed the box up the incline, but when we calculated it, it was 3 newtons up and 367 newtons down. So even though we were pushing up the incline, it was going down. So when we do the acceleration, the numbers will still say that it's accelerating, but all we have to say is, even though we're pushing it up the incline, all we have to say on the answer is the acceleration is, the number we calculate down the incline. So that's all we have to do with direction. We're not going to put negative or anything like that. But let's go ahead and let's draw this free body diagram. So let me get a triangle out. Okay. We've got our box here. More like a rhombus. I think that's what that's called. I don't teach geometry. Okay, but anyway, Let's color the box a little bit. Okay, messy. Comes straight down. You have gravity. Perpendicular to your surface, normal force. Straight down from normal force is Fg of y, and then making it 90 degrees with Fg of y is Fg of x. Now, we have an applied force up the incline of 3 newtons. We're going to have Fg of x, because we always do, because this is the only one that's acting down. That's why they're parallel to each other. They are the same thing. We just moved it up so we don't miss that calculation. I'm not going to write down net force because I don't know. I mean, I do know because I calculated it before, but I'm not going to necessarily write down net force because I don't know which way it's going to go, and that's okay. I'm not going to count on it if you don't draw net force. That's okay. I'm mostly, when you draw this, I'm looking for this one, and these. That's well, and this one too. But these are the ones that everybody messes up on, are these. Those are the 3 ones that they mess up on. Anyway, so it says, what is the acceleration of the box itself? Okay, so we need to determine, to define acceleration according to our equation we said earlier. Acceleration is equal to F net divided by mass. Well, let's go back to our question and see what information is given in the question. I'm given 22 degrees, I'm given 100 kilograms, and 3 newtons. Okay, so the 3 newtons is applied force. You can't really use it at this very second. I do have 100 kilograms though. Okay, that's our mass. Before, in the last question we did, it was in newtons, so that wasn't mass, that was actually weight. That's why we had to divide it by gravity again, is to get the mass. So I can go ahead and put this over here, go ahead and put 100 kilograms on the bottom. So that means all we're looking for to solve for acceleration is going to be F net. So let's solve for F net. Let's do that. So we've gotten used to writing equations for F net. We know that F net is going to be, let's look at this. There's no friction, but basically it's going to be F applied minus Fg of x. It's pretty much what it's going to be. So we know that F applied is 3 newtons. So we just have to figure out Fg of x. We've been doing that. That's not a problem. Fg of x is mass times gravity sine of the angle. So Fg of x is, let's see, mass was 100. Because this time it was given to us in kilograms, not newtons. So I got to go ahead and have my gravity out there. Sine of 22. Fg of x says, see, 100 times 9.8. I'm going to do that in a separate question. Times sine of, was it 12 or 22? I think it was 22. Yeah. Okay, gives me 367. Oh, that sounds right. I remember that now. Okay, so 367 newtons. Okay, so I'm not worried about direction yet because that's not my final answer. So I'm going to do 367 newtons up here in F net. You subtract those and you get 364 newtons. Now, remember, I'm not going to put my negative in there because that says direction. In physics, when you're dealing with motion like this, it means it's a direction, okay? We are going to say direction. We will not signify direction with a positive or negative in this thing because it starts to get a little confusing. Calculations go bizarre. So this would be 364 newtons down the incline. I'm not really worried about you writing that. I mean, you could. I'm not looking for your direction until the very end. And this is not the end answer. That's just net force. That's just going to go up here in that equation up there. So if you don't write down the incline there, that's okay as long as you write in your end answer. So 364 divided by 100, that's going to be 3.64, so that rounds to 4 meters per second squared. And this is where you say down the incline. And we knew that it was down the incline because we evaluated that it was 3 newtons up. Remember, it was 3 newtons up the incline and then 367 newtons down the incline. Here, like we calculated that. So 3 newtons down, I mean up the incline, 367 newtons down. So we evaluated that. So that when we gave a direction, when we gave the direction for the answer, we knew that it was down the incline instead of up. Even though the question said that it was pushing up the incline, the force going down the incline was so much that it was actually going down. Okay, so you've got to make sure that you pay attention to the question and you're doing net force that way too. All right, so let's try one now with friction. So this is going to be acceleration in 2D with friction. All right, so I pulled in this question that we did the other day. So the car is pulled up a slope of 12 degrees. The car weighs 3,000 newtons. If the coefficient of friction is 0.3, what is the net force on the car? So this question will change a little bit, and it will be worded as, what is the acceleration of the car? It says, and then the tension on the rope is 4,000 newtons. Okay, so let's go ahead and let's draw our free body diagram. So let's get our triangle in here. This is always step one. Draw your triangle. All right. So we have our, let's see, what are we doing? We're doing a car. So let's do a box for the car. Color in the box a little bit. All right, good enough. Okay, so everything goes straight down, always. That's FG. Let's zoom in a little bit. That's FG. Perpendicular to your surface is always normal force. Straight down from normal force is FG of Y. And then at a 90-degree angle from FG of Y is our FG of X. Okay, let's label our angle. Theta is 12 degrees. That means that this is also theta, which is 12 degrees. Now all that's left to do is what's going on up and down our incline. So we are pulling this car up this slope. So I'm going to draw this rope in black. Okay, there's a little wheel right here that pulls up on. So we have a tension force, because this is a rope, we have a tension force here. So that's F sub T. And then we have, remember that we've got to do FG of X, which is down the incline, FG of X. We also have frictional force, because we are going to have friction this time. But our net force is acting up, because it said that it is pulling it up. Okay. Now, what we've got to do is, the end answer is acceleration. So a lot of the time when you're given these problems, you don't know where to start. Okay, so figure out what it's asking for, and then you may have to kind of like connect the dots going backwards to see, this is the information that I'm given, this is where I need to be. Okay, so here's what I'm talking about. So the end answer is acceleration. Well, the acceleration formula we've been using for this is F net divided by mass. Okay, so let's look at our information in our problem. So I have 12 degrees. I have 3,000 newtons, which is our weight. I have a coefficient of kinetic friction of 0.3, and then I have a tension force of 4,000. So already, there's a little bit of information that we can already use is our weight. Now, we had to do this the other day where we had to take the weight divided by gravity, because we need mass, we don't need weight. So we do weight divided by gravity. So that'll be 3,000 divided by 9.8. That will be 3,000 divided by 9.8. 306. Let's just round the whole numbers just to make things easier. So mass will be, I'm going to pull this down a little bit. Okay, so mass will be 306 kilograms. So all we need to do now is find the net force. Well, we know how to write the formula for net force. We've been doing this for a while now. So net force is equal to the tension force minus, okay, we know that we need to subtract tension force because tension force is headed this direction. And then I've got two more forces headed down this way. So I got to subtract those. This is F net, so that's what we're trying to figure out. So it's equal to, so tension force minus frictional force minus Fg of x. All right. So we already have F net is equal to tension force, which is, the tension force is 4,000 newtons, minus, we need to find frictional force, and we need to find Fg of x. Okay, we can do that. All right, so let's find Fg of x is easy. Okay, Fg of x I know that we can get. So Fg of x is mg sine of theta. So Fg of x is going to be mass times gravity. Now, this 3,000 number here is already our weight. So I can go ahead and put that straight in because that's already mass times gravity. That is weight. So we're going to put 3,000 straight into here. So 3,000 sine of theta. Theta is 12. So 3,000 sine of theta. And theta is 12. So that gives me 624. So Fg of x is 624 newtons. So I'm going to go ahead and put that in here, minus 624 newtons. So all I've got to find now is my frictional force. So let me change something real quick, just a second. So I'm going to kind of color code these just to make things a little easier for you. Just because it's hard to keep track of what's doing what and what step is this. So let me color these real quick. So I'm going to change some of these colors of the calculations that we're doing. So just bear with me while I do this. This is one step. Let's find the acceleration. I'll make that orange. Net force, we'll leave net force red. Let's make Fg of x another color. Let's make this blue. Okay, so all we have left to do now is calculate frictional force. Well, we know, let's do frictional force in this green color. Okay, so frictional force is Fg of y times mu sub k. All right, so that's this one. So I'm actually gonna color this real quick. Let's do this in this color here, and let's color code Fg of x here, just to make things a little more we can understand. So this is Fg of x. This is 624 newtons. Okay. So that makes things a little bit easier for us since everything's kind of color-coded. So let's go back. Let me go to this green color. So frictional force is going to be Fg of y mu sub k. Well, I'm going to pull out another color because we got to do Fg of y now. Let's do yellow. So Fg of y, let me zoom in because you probably can't see this. Fg of y, remember the equation for Fg of y is always the same, so it's mg cosine of theta. Well, Fg of y, now our mg has already been given. We did it in Fg of x over here. Mg is 3,000 according to the problem. So Fg of y is going to be 3,000 cosine of, forgot the angle, 12. So Fg of y is equal to 3,000 cosine of 12, which is 2934. And that's in newtons. Okay, so we can now put this back in this equation over here. 2934 times 0.3 from the question, the coefficient of kinetic friction. So frictional force is 2934 times 0.3. 2934 times 0.3 is 880. All right, this is in newtons. Now, this is ready to go back in the equation for net force. That's 880 newtons. So all I do now to find net force is going to be to subtract. So F net is equal to 4,000 4,000 minus 880 minus 324, I think is what it was, 324, yes. Hit enter, and 2496 is what we're left over with. That's in newtons. Okay, so we have found the net force. We did that. In order to find the net force, we had to find tension force that was in the problem already. Okay, so it was tension force minus frictional force minus Fg of x. Okay, so tension force was given in the problem. Frictional force, we did this equation to find frictional force. Fg of y times mu sub k. Okay, mu sub k, if it came from the question, we had to calculate Fg of y. That's this one. All right, that gave us frictional force. Now, we also had to do Fg of x, which is this one here. So now we have our net force now. So now we can go back and we can do, let me get the right color here. We can put that in here. So F net was 2496. This is in newtons. Newtons divided by kilogram is a meter per second squared. So acceleration is 2496 divided by 306. That's going to be 8.16, but let's do whole numbers. So that is 8 meters per second squared up the incline. Okay, because remember we were pulling it up the incline. And that is your final answer, and that's it. Okay, so we're not necessarily going to say -8 because remember that's again its direction. We did say up the incline, so there's your direction. Okay, so if you need more help with this, let me know. I may have to work another example for you. Just, you know where to find me. This is one of the hardest concepts of the entire year. You just have to take your time. When you get ready to do this, there's a bunch of steps to go with it. Step number 1 is make sure you draw your free body diagram. Step number 2, let's start with acceleration because it's asking for acceleration. So let's do the formula for acceleration. That's F net over mass. So let's find F net. You know you need to find F net. You know how to write F net, the formula for F net. So you find that and you realize that there's a couple of more values you need to figure out, which is going to be frictional force and Fg of x. You know how to do Fg of x. It's mg sine of theta. So you know that one. So you just do frictional force, and that's going to be Fg of y times mu sub k. You then have to find Fg of y, and then you can do all that and plug it back into F net, plug it back into acceleration, and then you're good to go. So it's just a whole process. So if you need to rewatch this video and write down the steps that I do, do it. Okay? If you've got to do that, fine. You do what you got to do. Okay? Take care of business. You know what to do. You know what to contact me. Okay, have a good day.